Hi guys. In the last lecture we have seen about kinematics, which is one part of dynamics. In today's lecture let us see about kinetics, which is another part of dynamics. So we have seen the definition of kinetics, that it is a branch of dynamics which deals with motion of bodies considering the forces causing the motion. So if a body is traveling by application of force F and it is traveling with an acceleration A, it is mass m. If this force is considered in studying this motion of body, then it is called as kinetics. So how to solve these problems based on kinetics? There are three methods which are used to solve the kinetic problems. The first one is D'Alembert's principle, work energy principle, and the third one is impulse momentum principle. So in D'Alembert's principle, when acceleration is involved, we use D'Alembert's principle. When velocity and displacement are involved, we use work energy principle, and velocity time are involved, then we use impulse momentum equation. So let us see D'Alembert's principle first. It states that in order to make the body of mass m with acceleration a attain rest position, an opposite force called inertia force equal to ma is to be applied in direction opposite to the motion. So what it is saying is, by Newton's second law of motion we can see that if number of forces are acting on a body, there will be a resultant R. If F1, F2, F3 are acting on this body, resultant of this all forces will be R. This resultant force R makes the body of mass m move with acceleration a. This is what Newton's second law is saying. So according to Newton's second law states, if force R is applied, if force resultant, this is R is resultant, then the mass m moves with acceleration a. So then what is D'Alembert's principle saying? He is saying that if resultant is R, if number of forces F1, F2, F3 acting on this body, and resultant of all these forces is R, which makes the body of mass m move with acceleration a, in order to stop this body, another force ma should be applied in opposite direction to the direction of motion to keep to convert the body into rest. So this force ma is called inertia force. So when inertia force is applied, the system is said to be in dynamic equilibrium. It is said to be in dynamic equilibrium because whereas static equilibrium is the one in which equilibrium of the body is in rest position, whereas dynamic equilibrium is the one in which equilibrium of the body in motion. So D'Alembert's principle, according to D'Alembert's principle, if R is the resultant and inertia force is ma, which is in opposite direction to the direction of application of resultant, it will be equal to 0 since this is in dynamic equilibrium. So what is significance of this D'Alembert's principle? Let us see this. This inertia force does not act on the moving body. Actually, it is force exerted by moving body to resist the change in its state. So what it is saying is, if you are sitting in a bus If you are sitting in a bus and the bus is firstly at rest, if the bus suddenly starts, then you will be going backwards, because firstly you are at rest. According to inertia, the body tries to stay in its position, in its state may be rest or in motion. So this body is in rest first. By application of force, by application of force, this rest position is to be disturbed. That is, rest should be converted into motion. But inertia keeps the body, tries to keep the body in rest. That's why you lean backwards when the bus is started. This force, you move with an acceleration a. If your mass is m, and with the acceleration a you are moving backwards, the bus is moving with acceleration a, you are moving with acceleration a in opposite direction. So this is called inertia force. ma is called inertia force. This is what D'Alembert's principle is saying. So we can see that inertia force, the direction of inertia force is opposite to motion of the body. And if you are sitting in a bus and it is traveling with a velocity, and if it suddenly stops, you will be moving to front, because this bus is changing its states from motion to rest. But your body tries to stay in motion due to inertia. The inertia is resisting to change its state, right? So in order to come from motion to rest, the inertia is stopping you. That's why here there is decreasing acceleration, which means deceleration, which will be opposite to the direction of acceleration. And the acceleration with which you are moving front is a, and it will be a, or it can be represented as minus a, which is decreasing acceleration. So application of D'Alembert's principle. Let us apply this principle to a lift moving downwards and lift moving upwards. So there is a lift here, and here W is weight of the body, which is equal to sum of weight of lift and body. So if the weight is acting downward, this is just weight of the body. So if the weight is acting downwards and lift is moving downwards, if you if you are in a lift and the lift starts from rest and it is going downwards, you feel slightly weightless. This is because you are trying to stay in rest due to inertia, and the lift suddenly starts into motion. That's why you feel weightless. So according to D'Alembert's principle, the inertia force will be in a direction opposite to the direction of motion. Here in the lift, if it is moving downwards, the inertia force should be upwards, and the weight is always downwards because weight acts due to this gravity. So here W by G is M, right? M into A. There is a reaction, let us say it is R1. R1 is the reaction of lift surface. Reaction of lift surface due to weight of the person. Due to weight of person, which is W. So R1 is the reaction of the surface on the person. So if we consider the equilibrium, here R1 is upwards, considering the upward forces as positive, R1 is upwards, plus W by G into A, which is also upwards. The downward force is the weight of the body, which is W, which is equal to 0. So here R1 is equal to W into 1 minus A by G. So what is R1? The reaction of the surface on the person. W is the weight of the person, and A is the acceleration with which it is moving downwards, and G is the acceleration due to gravity. So what's the case in if lift is moving? Here lift is moving downwards. What if the lift moves upwards? So you can feel if you are standing in a lift and the lift suddenly starts moving up, you feel slightly more weight than usual. This is because due to inertia. So D'Alembert's principle states the inertia force will be in opposite direction to the direction of motion. If lift is moving upwards, the inertia force will be downwards. Here let us say this is the reaction is R2. If we balance these forces, upward forces as positive, R2 is positive and W is negative, and the inertia force W by G into A is negative, which is equal to 0. Then R2 will become R2 is equal to W into 1 plus A by G. This is the reaction by lift surface on the person. Next, let us see. Sometimes it will be asked like this. If the lift is moving downwards, there will be a tension and there will be a person here. Let us say W1 or let us say WT is equal to sum of weight of lift and weight of person. So WT is weight of lift and weight of person. If it is moving if it is moving downwards, the inertia force will be upwards, which will be Wt divided by G into A. And here W will be acting downwards, Wt. Here tension will be acting upwards, so balancing Wt into A divided by G is upwards, plus tension is upwards, is equal to minus Wt, which is downwards, is equal to 0. Here what will be the tension? T is equal to, taking Wt as common, 1 minus A by G when it is moving downwards. So when the lift moves upwards, you are staying in the lift. As it is moving upwards, the inertia force will be downwards. This will be Wt by G into A, and the weight will be Wt. The tension is always upwards. So what will be the tension in the wire? Upward forces are just T, and downward forces are Wt, and another downward force is inertia force Wt by G into A, which is equal to 0. Then T will become Wt into 1 plus A by G. So this is when lift traveling downwards, this is lift going upwards. So reaction of the surface on the person when it is moving upwards, reaction of the surface when it is moving downwards. So this is downwards, and this is upwards. So next let us see second principle, which is work energy principle. The first one is D'Alemberts principle. So second one is work energy principle. Work energy principle is used when velocity and displacement are involved in the kinetic problems. Velocity and displacement are involved in this. So what is work? Work is said as a product of force and displacement. So force can be a constant force or a varying force. When it is a constant force, the work done is force into displacement. When it is varying force, it will be integration of force into this unit displacement. If you see by a graph, what is a constant force? For some time t, the force should be constant. So this is the constant force, right? The area under the force and time curve gives the work done. Whereas in varying force, in the given time t, the force value changes like this according to some function. So if we consider a small displacement ds, sorry, this is displacement s. And this is also s. So what is constant force? In the travel of body from one position to another position, for example, it travels at a it travels distance s in time t, and the force along this travel remains constant, then it is constant force. If it varies along the distance and along the distance s or displacement s in the time t, it varies like this. according to the function. Let us consider a small displacement, elementary displacement ds, like this, and if we expand this elementary area to the entire force displacement diagram, we will get integral f ds. So what is energy? Energy is the one that it is defined as the capacity to do work. We have seen in the introduction chapter that all this term work and energy. There are different types of energy like mechanical energy, hydraulic energy, electrical energy, but we restrict to only mechanical energy here. Mechanical energy has two types, which is potential and kinetic energy. We have seen from the definition of mechanics that it is the study of body which is in rest and which are in motion. So bodies at rest, energy possessed by bodies at rest is called potential energy, and bodies in motion, energy possessed by bodies in motion is called kinetic energy. If there is a body on top of a building and it is to be thrown onto the ground, so what is the energy possessed by this body at this top of the edge, which is W into h, if this is height h. If this is height h, the energy possessed by this body is called potential energy, and it is equal to W into h. W into h is the energy potential energy possessed by the body. So what is kinetic energy? If the body is traveling with a velocity v, the energy possessed by this body at this instant, at this instantaneous velocity v, is called kinetic energy. It is going to do some work, right? It is called kinetic energy, which is half mv square. M is also written as W by G, right? So work energy equation for translation. Let us see what is work energy equation, which we are going to use to solve the problems of work energy equation. See here, a number of forces are acting on this body. F1, F2, F3 are acting on this body, and initially it is at velocity u. It is traveling with a velocity u. Due to application of force, say resultant R, resultant of all this F1, F2, F3 forces is R. It reaches to a position, second position. Here firstly it is at position number 1 and it reaches position number 2 after traveling a distance s, and it reaches to a velocity v. Firstly it is traveling with initial velocity u, and a force R is applied, and it travels up to 2. It reaches velocity v. So for this, work energy equation can be written as the work done is R, the force into the distance travel. It is the work done. What is the energy? Energy to do this work is, the body has half mu square energy at position number 1. Here it has half mv square energy. This is kinetic energy. The change in kinetic energy is the actual energy to do this work. So change in kinetic energy is given by half mv square minus half mu square, which is half m into v square minus u square. So work and energy have equal units, and this work is equal to change in kinetic energy. So R into S is equal to half m into final velocity square minus initial velocity square, which is equal to half into m can be written as W by G into V square minus U square. This is work energy equation. Let us see a problem based on work energy principle. A body moving up the plane with initial velocity 1.5 meter per second is applied with a force 400 Newton up the plane and it travels 6 meters. Find the final velocity of the body if mu is equal to 0.2. First we need to identify by which principle we need to solve the problem. Here velocities are involved and displacement is also involved, so we need to apply work energy principle. So what he is saying, there is a body traveling up the plane. First it has initial velocity of 1.5 meter per second. It has initial velocity of 1.5 meter per second and it travels a distance. So initial velocity is 1.5 meter per second and it travels a distance s is equal to 6 meters up the plane, and it has mu is equal to 0.2, which is coefficient of friction between the body sliding and the inclined surface is 0.2. And what is asked to find? The final velocity v is asked to find. The force applied is 400 newtons and the weight of the body is 300 newtons. The angle of inclination is 30 degrees. So the weight is acting downwards here, and if we resolve this weight into components along the plane and perpendicular to the plane, this will be opposite to the theta. This is theta, which is 30 degrees. Opposite to the theta, this is W sin theta, and adjacent to the 30 degrees is W cos theta. And there will be a normal reaction perpendicular to the surface and frictional force acting downwards. This is because the body is moving upwards, the frictional force will be downwards. So if we balance these forces, let us say sigma f normal is equal to 0. Balancing the forces perpendicular to the plane. What are the forces perpendicular to the plane? There is force N and weight W cos theta. These are the perpendicular forces to the to the plane. So N is equal to W cos theta. So what is N? W is 300 and cos theta is 30 degrees. We get 259.81 newtons. From this we get frictional force is given by F is equal to mu into N, and mu is 0.2 and N is 259.81. So we get frictional force as 51.96 Newton. So what do we need to find? We need to find the final velocity, right? So from work energy equation, what is work energy equation? Resultant into displacement is equal to half into W by G into V square minus U square, right? So here what is resultant? The resultant will be of 400 newtons and this W sin theta. This is in this direction. The forces should be considered because the motion is in this plane, so we need to consider forces along this plane. So what are the forces along this plane? 400 newton and W sin theta, and frictional force F. The forces upward the plane, let us take forces upward the plane as positive. 400 newton is acting upwards. 400 newton is acting upwards, and the downward force is frictional force, and also W sin theta is acting downwards. The distance moved S, which is equal to half into W by G into V square minus U square. So 400 minus what is F? 51.96. 51.96 minus W is 300 newton and sin theta is 30 degrees into the distance traveled is 6 meters, which is equal to half into weight is 300 and acceleration due to gravity is 9.81. Here it is V square minus initial velocity is 1.5 square. So we get final velocity as 8.942 meter per second. This is how we need to solve the work energy. We need to solve kinetic problems using work energy principle. And there is work done by a spring. So if there is a spring, and it is applied with a force F and it is compressed to a position like this, let us say this distance is some x. So the ratio of force and this distance gives the spring constant, and this spring constant is constant for a particular type of spring. So ratio of force applied to the length compressed is called spring constant, and the spring constant is represented with K. K is equal to F by X. So work done by spring force. If it is compressed, the force is acting on the spring, right? And the spring is doing work against this force. So it will be minus half into K into x2 square minus x1 square. It is given by work done by the spring force is given by half into K into x2 square minus x1 square. This is because F is equal to K into x. F is given by K into x. What is the work done? Work done is given by the force into displacement. Here it is, force is K into x and the distance is x. So it is kx square. Then what is x1 and x2? Firstly, if it is already, this is the original position. Let us say this is original position, undeformed position. If it is initially in a compressed state x1 and a force is applied, due to this force it is compressed to a length x2. So the work done by this force on the spring is half into k into x2 square minus x1 square. The work done by the spring is, it will be minus sign here because it is against the work done by the force. So x1 is initial deformation, x2 is the final deformation. So next one is impulse momentum method. When is impulse momentum method is used? When velocity and time are involved in the kinetic problems, we use impulse momentum method. Let us see impulse and what is momentum. Impulse is the one impulse is equal to force into time. When a force is applied for a small time and this force is multiplied by the time applied, it is called the impulse. And what is momentum? Momentum is product of mass and velocity is called momentum. Suppose there is a body here. This is a body of mass m and there is a force r is applied for a small time t and it reaches from velocity u to v. Then from this, so r is equal to m into a, we know that by Newton's second law. Acceleration can be written as rate of change of velocity, right? Rate of change of velocity is acceleration. So if we take dt this side, r into dt is equal to m into dv. Integrating both sides, we get integral r dt integral m dv. So the force is applied from 0 to t seconds and velocity changes from u to v. These are the limits for force and limits for LHS is 0 to t and the limits for RHS is u to v. This is for variable force. Varying force we need to integrate that, but if the force is constant, then r comes out of the integration, and integration of a constant dt is here, it will be t and the limits are 0 to t, and here it is m into v minus u, it is mv minus mu, and here this is the impulse momentum equation. RT into mv minus mu is impulse momentum equation. Here RT is impulse and this is change of momentum. How to solve these problems? Here a question is given. A glass marble whose weight is 0.2 newtons falls from a height of 10 meters and rebounds to a height of 8 meters. Find the impulse and average force between the marble if the time during contact is 1/10th of a second. So there is a marble here which has weight is equal to 0.2 newtons. Weight of this marble is 0.2 newtons. Let us say this point is A and here it is ground. It travels from height A and reaches the ground B, and it again travels upwards and it reaches a point B which is 8 meters from the ground. Here it is dropped from a height of 10 meters it is hitting the ground and it is reaching and rebouncing up to a height of 8 meters. So what is he is asked to find us? Find the impulse and the average force. Impulse and average force. So how to find this? So impulse momentum equation is RT is equal to mv minus mu. This is the impulse momentum equation. Considering this position, it is hitting with a velocity of u. This is initial velocity with which this body is hitting the ground when it is first coming to the ground, and it is rebouncing. This is hitting velocity, initial velocity u, and it is moving up to a height of 8 meters. It is final velocity v, which is upwards in direction. So in kinematics equation we have seen that v square minus u square is equal to 2gh, right? If the body is falling downwards and as the body is dropped, initial velocity will be 0, right? Which is 2 into g into h. So v is given by under root 2gh. So considering the 10 meter one, we get u is equal to, u will be the final velocity, right? For this, it will be the final velocity. So u is equal to under root 2gh, which is equal to 2 into 9.81 into 10 meters is the height. So we get u as 14.007 meter per second. This is the initial velocity with which the body is hitting the ground. After the body hitting the ground, it is traveling up to a height of 8 meters. So when the body is traveling, v square minus u square is equal to 2gh, right? When the body is traveling upwards, here the final velocity will be 0 because the body travels from this ground position to this B, and again it falls to the ground. So here the velocity will be 0. The final velocity is 0 minus u square with velocity with which the body is thrown up is equal to, here g will be minus because it is traveling against to the gravity, which means it is going with a retardation and not acceleration. So u will be under root 2gh. So in this kinematic equation, the initial velocity with which the body is to be thrown up is under root 2gh. In this case, the body is to be thrown with a velocity v. The body is hitting with a velocity u. The body is to be thrown. The body for 8 meters, it is to be travel with velocity v. So here v is equal to under root 2gh. Let us say this is h1, which is 10 meters. Let us say this is h2, which is 8 meters. So under root 2 into 9.81 into 8 meters. It is traveling 8 meters with a velocity v. So v will be the velocity with which it is thrown, and it is 12.528 meter per second. This is downwards, this is upwards. If we consider the impulse momentum equation, RT is equal to mv minus mu. We need to find this impulse first. Impulse is equal to RT which is equal to, what is the mass of the body? The weight is given as 0.2 newtons. W by G is the mass of the body, and it is, what is the final velocity? V is 12.528 minus, what is U? It is 14.007, which is downwards. Let us say this V is upwards, right? Taking upwards as positive and downwards as negative, we get it as 0.541 Newton second. Units of impulse is Newton second. So we got impulse RT is equal to 0.541, and it is also asked to find that the force is equal to 0.541 divided by T. So the time is given as, find the impulse and average force between the marble if the time during contact is 1/10th of a second. So the contact between the marble and the floor is 1/10th of a second. It is 1/10. The force is 5.41 newtons. This is how we need to solve the kinetic problems with help of impulse momentum equation. So what we have seen today, how to solve kinetic problems using D'Alembert's principle and work energy principle, and another one is impulse momentum equation. If this video is helpful, please like, share and subscribe this channel.